I want to talk about rotating rigid objects. And there's really three ways that you can rotate a rigid object. And I've done this before, but I want to show you this code. And I'm not going to build the code. I'm going to show you the code. I'm going to show you some more code. So this is what I call the 3-mass rotator. I'm going to play it. So we have these 3 masses, then they're rotating, and that's pretty awesome, right? Okay. Now, how can we make a rigid object like this rotate? In this case, what I am doing is calculating the net force on each object. This is not a rigid object. This is a springy object with very stiff springs. So I have these 3 masses. They're connected by springs. I calculate the spring force, the net force on each one, and it just rotates, and which is kind of cool, okay? Now, we can use this, and this is kind of awesome, we can use this to demonstrate the property of this flipping T-handle thing. And I've made a video on this before, but I'm going to show you. So if I rotate it, that's rotating with an angular velocity in the x direction. If I give it a little y value of the angular velocity, let's just see what happens. So in this code, let me show you the code real quick because I want to show you that it is indeed real. So there's nothing important there, graphs. This is just the lengths of all the sides. Here's my initial angular velocity vector. I called it omega. I changed that to W later. K is the spring constant between all the things, the center of mass, and then I have these masses right here, right? They're just 3 masses, and they all have an initial velocity. Now, this is the hard thing, right? How do you calculate their initial velocity based on the angular velocity? That's a little tricky, and that's not terrible, right? Going the other way becomes impossible if you have large objects. And then this is RAB, RBC, RCA, are just the vector positions between all of those so that I can calculate their unstretched lengths. I want to make those lengths for the springs. And then I have the 3 springs, the unstretched lengths. And then down here, I'm just calculating these 3 forces, right? The 3 spring forces, each mass has 2 of these forces acting on them. Update the momentum, update the position, and let it rock and roll. And so that's what it does. But now let's go back up here. Yes, I'm going to give you the code. You know I'm going to give you the code. You knew that. Why are you even asking? Okay, let's give this an initial velocity of 2.2 in the y direction, and let's run it and see what happens. So now you can see that it actually tumbles and it flips directions when it rotates. The key here is if it's exactly lined up, then it's stable rotation. But if you tilt it just a little bit, it's going to rotate and flip over the other way. And that's fun to play with. And there's no angular momentum here. This is just forces, and that's what I love. Okay. Now, let's think about another way to model the motion of a rigid body in Python. Let's do that. Okay, I'm switching over here to the board, and we're going to talk about some physics, and then I'll show you my code, which I've already built, right? I'm not going to build this live. You know I like to build things live, but I'm not building this live. So suppose I have a rigid object. Let's say it's a cube or a rectangular cube like that. The number one thing that I just showed you is that you could model this as individual masses connected together and just use forces, and forces show the rotation of a rigid object. Okay, that is an important point. But I can also use the angular momentum principle. This says that the net torque, I'm going to assume a center of mass is at rest, and I'm going to assume the center of mass is at the origin just to make things easier. The net torque on the object is the rate of change of angular momentum. And so I have no torque on my system. So there's my center of mass. So L is constant. That's important. Now, how do we write L? We write L as I omega, where omega is the angular velocity, L is the angular momentum, and so this is going to be constant. Now, if I have a rigid object that's not rotating about a fixed axis, then I is not a scalar value. I is the moment of inertia tensor. So we can write this moment of inertia tensor as this. It's a 3 by 3, I x x, I x y, I x z, I y x, I y y, I y z, z, I z x, I z y, I z z. Okay. So when I take that and operate this on the angular velocity vector, which would be omega x, omega y, omega z, I might get a different angular momentum. So L and omega do not have to be in the same direction. Okay, so that's important. Now, well, how do you find all these elements of the moment of inertia tensor? Well, if these are finite points, which I'm going to deal with just a finite point for my rigid object, we could integrate and do something else later, then I can find the diagonal elements with the double things on there, like I, X, X. That's going to be the sum over I, mi, is basically the moment of inertia of about a fixed axis in the x direction. So r squared is going to be y squared plus z squared. It's not going to be x squared. So it's going to be yi squared plus zi squared. And so I can find Iyy is going to be mi xi squared plus zi squared, and zz is x squared plus y squared. Now for the off-diagonal elements, such as I, x, y, they're going to be negative the sum over I, mi, xi, yi. So that one, I, y, z, is going to be negative mi, yi, zi, and so forth. So we can calculate all those things. Now, how would we model the motion of this rotating object? That's the question. And there's no torque. I want to do the same thing. I want to show something that's rotating and flips over. Okay, so we have a bunch of work to do here, but we're going to do it anyway because it's fun. So if L is constant, what I'm going to do is I'm going to take some initial angular velocity vector omega. I'm going to calculate the moment of inertia tensor. And then I can use this. If I operate that moment of inertia tensor on the angular velocity, I get the angular momentum. Fine. Once I have the angular momentum, and once I have the angular velocity, what I can do is to rotate this about that angular velocity, using that angular velocity. But then my moment of inertia tensor changes. So I have a new moment of inertia tensor in the reference frame. Here's what we're going to do. I want to break this into time steps, use omega to rotate the object, and then calculate the new moment of inertia tensor, assuming L is constant. So, but how would I get the new angular velocity? If I know I and I know L, I have to find the new omega. So here's where we're going to have to find the inverse of the moment of inertia tensor. So if I take the inverse of the moment of inertia tensor and operate that on both sides, this one becomes identity matrix. So omega is going to be L, it's going to be I inverse L. And L is a constant, so I need to recalculate I each time and then use that to find the new angular velocity. With the new angular velocity, I can rotate the object and then calculate the new moment of inertia tensor again. Okay. Whew, that's a lot of work. Now, the problem is I like to use WebVPython. WebVPython doesn't have matrix operations in there. It has vectors. It doesn't have that. Okay. So I'm going to have to build some stuff here. Let's talk about how we build a couple of things. Number one, how do I represent a matrix? How do I operate a matrix on a vector? How do I find the inverse? Oh, look at that. The inverse of a matrix, which I have to find the determinant. And there are some places where this doesn't work. And then my goal is after this, not now, maybe today, make another video to show you the third way to rotate a rigid object. So that first way is rotating this by connecting these as springs, right? So rigid E, and then using the moment of inertia tensor, and then we'll do it another way, which is weird. I haven't figured it out yet. Okay, so let's suppose that I want to do I omega. I want to find L is I omega. How do I do that in Python? Well, I do have the vector class in WebVPython, so they'll have those as vectors. What I'm going to do is to represent I as a list of vectors. So I'm gonna put it in a weird notation. I'm gonna call this IX vector, IY vector, IZ vector. And that's really just, I'm gonna write one of them out. This is gonna be the vector IXX, IXY, IXZ. And then I'm gonna do the same thing for the Y and the Z vectors like that. Now if I want to operate that on this, what I'm going to get is L is going to be the vector ix dot, it's a vector, dot omega. The y component is going to be iy vector dot omega, and then iz dot omega. So I get another vector by taking the dot product with my list. Okay. That's my matrix multiplication with a vector, and that seems to work. So I can use that to get L. Okay. Now how do I get the inverse? So the first thing is to get the determinant, and I don't really want to write down the equation, but I want to point out something really important with this matrix. So here I have ixx, ixy, and then I have other numbers, and then here I have iyx. So this is going to be, I'll put these in here, iyy, izz. So notice that this term right here, yx, is going to be the sum of the mass times its y times its x, negative. And this is going to be mass times x times y. But multiplication, you know what this means, right? That means commutes. So this number is the same as that number. And this number, so I can really write my moment of inertia tensor like this. A, B, C, B, D, E, C, A, B, C, E, A, B, C, D, E, F, is that A, B, C, D, E, F. So it's a symmetric matrix, right? So I really only have those 6 values that I care about. And you don't have to do that, but it makes my calculations a little bit easier because I'm going to take the determinant and then use that to find the inverse, which I don't really care about doing that manually. I'm just going to write down the equation. Let me show you my other program that does this, and we're going to go through all the steps, okay? And then I'm going to show you where it doesn't work. That's what I'm going to do. Okay. So let's go to right here. So let's just run it, and then I'll show you it all. So this is a cube, and I made my cube. It's not an actual rectangular cube, although it could be, because I don't really care. I'm not doing any forces. It's just angular momentum. I'm going to use these 4 masses to calculate the moment of inertia tensor, and then use the angular velocity to rotate it, find the inverse moment of inertia tensor, and then use that operating on the angular momentum to find the new angular velocity. So let's just show it running, because it's kind of cool. So I have 2 arrows here. I have a cyan arrow and a yellow arrow. Yellow is the angular momentum. Cyan is the angular velocity. And they're basically in the same direction, so this thing rotates as you would expect. And I have the 4 corners there. The box is just there for visualization, and it does look kind of cool. Okay. Let's go over all the important parts of the code. And for some reason, right there. Does he see the bottom? Okay, there's the bottom. Okay. So the mass, m is just a mass, and that's my angular velocity vector. R is just the size. Now, one of the ways I'm going to calculate moment of inertia tensor, one of the ways I'm going to calculate all my stuff, I'm going to have a list of all my masses. So I have 8 masses, and I just did this manually. It wasn't too hard to do. I have 8 masses for the corners of that rectangular cube. So they just have a mass, and they have a position. And it's not a complete square, right? It has different dimensions. And then, they give it a radius for the spheres. I give them different colors. Make trail equals false, because what I'm going to do is make it where it makes sense and then move it so that the center mass is at the origin. So I'm going to not have the trails on during that move. I don't want to see those. Retain 50 just says don't keep all the trails. Retain only 50 points. And then they have different colors just so you can see how it flips. And then down here, what I'm going to do is to add all those masses to a list. So I have a list of 8 masses, and that just allows me to go through and calculate the moment of inertia tensor. So this first function is the moment of inertia tensor, and I call it ID. And I changed this a couple times, but I gave it a list of masses and a point about which to calculate the moment of inertia tensor. So that's more generic, right? We don't have to calculate the moment of inertia tensor about the center mass, but I did. So in order to do that, I'm gonna have this sum, right? Ixx is the sum of mi times xi squared plus yi squared. So if I want to sum something, I have to start with a value of 0 so I can add things to it. And the same things for the other components, the elements. Now you'll notice I only have 6 of these. I have an ixy. I don't have an iyx. Again, because it's the same thing, right? I don't have to calculate it twice. So here's my loop for m in masses where I go through all the masses. And what I do is the first thing is to calculate the vector from the point where I want to calculate it to where that mass is. So if it's not the origin, then it's whatever point RO is. And that's what that vector is. And then I can just calculate Ixx is going to add on, that's why it's a sum, m r y squared rz squared. And then here the yx is going to be negative m rx rz ry and so forth. So you go through and do that. And then after I go through all the masses, I set the vector ix to ixx, ixy, ixz, and same thing for iy and iz, and I return this as a list. And that's that. Okay. So that gives me the moment of inertia tensor. If the masses rotate, then I can redo the moment of inertia tensor. And that's why it's better to do this with these masses instead of an integral. You can still integrate, but I'd have to reintegrate every time I rotate the thing. And so there's another way to do it, but this is the way I'm doing it now. Okay. And it works. It's kind of cool. This function, vmult, is a vector multiplication. So I'm going to take the matrix A and the vector B and operate them together. Okay. So, and just like I said, the result is going to be a vector, right? So the vector is going to be called C. So the x component of that is the first element of A, the matrix A, which is A0 dot B, A1 dot B, A2 dot B, and then return that vector CX, CY, CZ. That works fine. This is the determinant of the matrix. You give it a matrix A. So the first thing, I wanted to use my same notation here. A, B, C, D, E, F, G. Why do I have G? I don't have an F. That's weird. Okay, that's fine. It worked. I told ChatGPT to give me the determinant of the vector A, B, C, D, E, G with the dot, with symmetrical, and it did. So I just used their formula right there. But I need to make the translation between the matrix, which is a list of vectors, and the component names A, B, C, D, E, G, which is weird. So that's A0.x is that first element. A1.y is, oh yeah, so I don't have all the elements because they're symmetrical. But then it returns that value right there, and then the inverse takes the determinant. I need to take 1 over the determinant, and I can get the x, y, z components right there. Now right here, I'm going to calculate the center of mass. So I'm going to take the center of mass as a sum, so you have to start with the 0. So I'll take 0, the vector 0, and I'm going to add m times r for all the things, and divide by the total mass. So I need the total mass too, which I knew what it was, but I did it anyway. So this calculates the center of mass, and then right here, this stuff moves all the positions so that the center of mass is now the origin. I recalculated the center of mass right here. I'm not sure why. Oh, because it moved. And so I just want to make sure it was 0, right? I can't leave the center of mass where it was once I move all the objects. And then I go down here and I go through all the objects and I turn the trail back on. So L scale and W scale are just these scaling factors for the lengths of those arrows. I'm going to draw arrows, right? But arrows have actual size. So I need to give a translation between length and size. I calculate the moment of inertia tensor for the initial state using the moment of inertia tensor. And then I calculate the angular momentum using my initial angular velocity. And then I make those two arrows. And this OB is just a box, right? It looks nice to have that box so you can see the shape. If you just look at the points, it's hard to see that they stay in the same shape. So I put the box there. Okay, so now my loop isn't too bad, right? I need to do number 1. Calculate every time step. Calculate the moment of inertia tensor. I did that. Calculate the inverse of the moment of inertia tensor. That's what we're doing right here, right? I give it the value I, and this is why I called that function ID, because I wanted to call the moment of inertia tensor I. And now I'm going to calculate the angular velocity. So I'm going to assume the angular momentum is constant. I'm not going to change that. So I take the vector multiplication of I and L, and that gives me my new angular velocity because the moment of inertia tensor changed. And then I'm going to draw my arrow. Now right here, what I need to do is to take all those masses. I know the angular velocity. So I'm going to use the angular velocity vector, the direction. In WebVPython, we have a really nice rotation function, right? So there you can just rotate an object if you give it an axis, an origin, and an angle. So my axis is the unit vector omega. You don't even have to give it a unit. The origin about what I'm going to rotate is my origin, vector 0, 0. And then the angle is omega dt, right? That's going to be my how far it rotates. So I calculate the magnitude omega, multiply it by my time step, and that's my angle that it rotates with. And then my axis is just the angular, the unit vector omega. And then I rotate my box too. So that's it. So this is really kind of cool because there's really not that much to do, right? Well, there's a lot of matrix stuff in there. Calculate I inverse, use that to find omega, rotate stuff, and then do it again. And it works. Okay, so let's show you how it works. I'm going to make it flip up here. Where's my angular velocity? I'm going to give you this program. Don't worry about it. So this is, if I rotate this in the x direction, I think I need to rotate it. You need to rotate about the middle moment of inertia. Let's see. So that's the middle one, I think. Let's see. So it's r by r over 2 by r over 4. So I need to rotate this in the y direction. So let's put this at 0 and then put this at 1. I think that'll work. So you can see that that angular velocity vector is deviating away from the angular momentum vector, which stays constant, and the whole thing's going to flip over. I mean, I'm kind of happy about this. It's pretty cool. So does it flip all the way over? It should. Maybe it'll do that eventually, but it's definitely doing stuff. I think this is working fine. I should get the angular velocity vector going all the way down, but anyway, I think it's working just fine. Okay, and it's pretty cool. Now I want to show you a case where it doesn't work. Here's another 3-mass rotator. And what I want to do is to display the angular momentum and the angular velocity. This case, I'm actually calculating the forces, right? So it's back on the spring force one, but I wanted to, in order to calculate the angular velocity vector, you have to do the same thing. You can't just say what it is. You got to use the inverse matrix of the moment of inertia tensor. So if I give this a large deviation, let's say, I'm going to guess 0.3. Oh, let's just make it rotate about not the z-axis. It's very stable on the z-axis. But you'll see here, it just blows up, right? So what's happening is we're going to get to situations where the determinant of my moment of inertia tensor is close to 0. And then so that's going to make it so you really can't find an inverse to the matrix, and it doesn't really work. And that's where I want to go with the next thing. So there's another way to rotate rigid objects. Hopefully I'll get it to work, but I don't want to promise anything because I haven't figured it out all the way yet. But I want to make this video and show you the problems with rotating rigid objects and a couple of solutions. So these two solutions mostly work. Definitely if you have them connected by springs, works. If you use a non-degenerate rotation mass, it should work. And if in some cases that flat mass doesn't work, so we'll have to work on that with another method. But there you go. These programs will be down below. Hope you enjoyed that. I'll talk to you later. Let's do some more physics. I needed like a good ending line to think about, and I don't have it, but we'll get to it. Okay, later.